Welcome. This is section 7.2, proofs about graphs and trees, and today we cover day 1 of 2. Today, in this video, we'll look at some direct proofs and inductive proofs for several graph theory results. And in fact, by the very end, we'll get a proof of Euler's theorem, the theorem that any graph where all the vertices have even degree must have an Eulerian circuit. There is a lot in this lesson. A lot of lemmas, propositions, and theorems to cover. The first 4 can be handled with direct proof, and then the later 4 are handled with proof by induction. So it's kind of cool. It's one of the nice things about this lesson is we get to see a lot of different proof techniques in graph theory. In direct proof, we'll only actually prove proposition 2 and 4. And in the proof by induction, we will cover the proofs for the remaining 4 results. I'm really just mostly interested in proof appreciation for this video. I will not ask you to reconstruct proofs or to memorize anything, but throughout this video, challenge yourself, see if you can understand every step of the process and understand the reasoning that goes behind these proofs and appreciate the results that we can get from the application of logic to graphs. To begin this big section 1, direct proofs of graph properties, there are 3 important ideas that we keep cycling around to again and again and again. That's connectedness, cycles, and trees. A few definitions to begin. G is connected if there is a walk between any 2 distinct nodes. So let's take a look at this example graph that I have here on the screen. Pick 2 random nodes. How about that one? There, I'll call that V, and over here, W. Can I make a walk that goes from V to W? I think I can. Here we go. How about something like this? Come over there and down, and then come down to W. There we go. It wasn't maybe the most efficient walk, but there was a walk. And the fact that I can do this for any 2 distinct nodes means that the graph is connected. Next, recall that a path is a walk with no repeated nodes. So I could make a path. Again, let's call this V, and this one will be W, and there is a nice path that goes from V to W. There we go. Something like that. A cycle is a circuit with no repeated nodes. So I could make a circuit, maybe that looks something like this. But of course, a circuit is allowed to have repeated nodes. But to make a cycle, maybe a cycle looks something more like this. There we go, that's a nice cycle. So the key idea for paths and cycles, remember, these guys have no repeated nodes. On to some theorems on connectedness. Lemma 1. Recall a lemma? Lemma, that just means it's a result that maybe it's not so interesting on its own, but it is a helper result. It helps us prove larger, more interesting results later on. So here's lemma 1. A graph G is connected if and only if, for every pair of different vertices A and B in G, there is a path in G starting at A and ending at B. This lemma is a consequence of proposition 6 to be proven later. So we won't actually prove this lemma. It results as a consequence of something later on. But notice how the lemma really looks almost like the definition for connectedness. The only difference is that this lemma says, you know what? You don't have to use a walk. You can use a path if you want. Okay, let's move on. Proposition 2. Suppose G is a simple graph. So simple means no multiple edges, no loops. And A and B are vertices in G with no edge between them. So for example, maybe here's A and there's B, 2 vertices with no edge between them. Let G prime be the graph formed by adding the edge AB. All right, so here we go. I'll add an edge AB. Proposition 2 says, if G is connected, then G prime has a cycle that contains the edge AB. Now, in the picture, the original graph G was connected, and so this new thing, you can probably see it, there are lots of cycles that contain my new edge AB. In fact, you might even be able to think how the proof goes. Since the original graph was connected, there's a path from A to B. Let me draw one out. Here's a path from A to B. There we go. And then by completing the path and connecting the edge A to B, I end up creating a cycle. Let's see the proof officially. Proof. Since G is connected, there is a path from A to B in G. This was our lemma 1. And so the path might look something like this. A, and then some vertex, and then some vertex. I list a bunch of vertices, and then B at the very end. Thus, if I take that same path and I append A to the end of it again, now I have a cycle. A cycle is a path that begins and ends at the same vertex. All right, that's it. Starting off easy. Proposition 3. When an edge is removed from a cycle in a connected graph, the result is a graph that is still connected. So take a look at this graph. Here's our example graph. And I will identify a cycle. So how about something like this? Here's a cycle in the graph. And I will remove that bottom edge. The proposition is telling us that this result with the edge removed is still connected. And that should seem reasonable because, after all, I still have most of my cycle remaining and that's all connected together. Let's see the official proof. There is no official proof. This is left as an exercise. Think about this one and see if you can come up with a proof for it. Proposition 4. If every vertex of G has degree 2 or more, then G contains a cycle. This one is interesting. I know something about the graph that will guarantee the existence of a cycle if every vertex has degree 2 or more. Kind of a neat result. So this graph before us, you can see every vertex does have degree 2 or more. And yes, indeed, there are many cycles. Here's an idea for how the proof is going to work. Pick any vertex. We'll call it v sub 0. So starting on the bottom left, v sub 0. Since this has degree 2, there are 2 ways that I can leave it. I have some choices. So let's just pick one of those ways and follow where it goes. And the vertex I arrive at, we'll call that v1. v1 has degree 2 or more. So I can leave v1 along a different edge than what I came in on. So I'll leave in a different direction. And I come up to a next vertex. We'll call that v2. The degree is at least 2. So I can always leave along an edge that I did not come in on. So let's go here, and where I arrive, I'll call that v3. I can leave the vertex along a different edge. Let's come down. We'll call this result v4. I can leave along a different edge. We'll come back. And look at this. At this point, I revisit a vertex. But I'm going to do something interesting. I'm going to continue my labeling. I'm going to call this v5. And I can leave along some edge other than what I came in on. And so on, v6. And I can continue. And the idea is that if I do this long enough, I will be forced to double back on myself at some point and find a cycle. All right, that's the idea. Let's see the official proof. Let n be the number of vertices in graph G. Let v sub 0 be any vertex in G, and let v1 be one of its neighbors. Now, the word neighbor, that is official graph theory terminology. If I have 2 vertices that are connected by an edge, then we say that those 2 vertices are neighbors. Let v2 be any neighbor of v1 other than v0. And I know I can do this because the existence of v2 is guaranteed by the hypothesis, the fact that every vertex has degree 2 or more. Let v3 be any neighbor of v2 other than v1. Let v4 be any neighbor of v3 other than v2. And so on and so on. Let's continue this until vertex v sub n is identified. And look, I have v0, v1, all the way up through vn. That's n plus 1 vertices. But I know that there are only n vertices in the graph. So by the pigeonhole principle, there has to be a repeat among v0 through vn. So let's find the first repeat. Now, technically, we do this by finding the least j, so that vi equals vj for some I less than j. But that's the idea. Find the first place in this list where there's a repeat. And then just take that repeat and make that into a cycle. So vi is the same as vj, and I won't have any repeats in between I and j. And so there we go. We have found a cycle. Proposition 4 has some nice different ways of interpreting it. Let's take a look at the contrapositive. It says, if G contains no cycles, then there is a vertex of degree 1 or less. What does a graph with no cycles look like? Maybe, here we go, something like that. There's an example of a graph with no cycles, or you know what, even just the single vertex, the graph that contains one vertex and no edges. There we go, that contains no cycles. We could improve this result a little bit by saying, if G has no cycles and if G has at least one edge, so that's kind of eliminating the trivial case, then some vertex has degree 1. And in our example, we see several vertices here that all have degree 1. And this leads us to the definition of what we call a tree. A tree is a connected, simple graph that has no cycles. Vertices of degree 1 in a tree are called leaves. So I am allowed to have the trivial tree, the tree that consists of just a single vertex. But take a look, in all of these examples, the defining characteristic is that there are no cycles. In every case except the trivial case, I'm definitely guaranteed to have at least one vertex of degree 1. Alright, and this brings us to induction proofs of graph properties. Let's see how we can use induction. We have 4 results that we'll look at, 2 propositions and 2 theorems, including the big Euler's theorem. We'll use induction to prove that result. Let's get to it. Proposition 5. If G is a tree with at least one edge, then G has at least 2 leaves. So this is an improvement on Proposition 4. Proposition 4 said that any tree has to have at least one vertex with degree 1, but this proposition says, well, you know what, in fact, we'll find 2. All right, let's see how this works. Let n be the number of edges in my tree G. And we have a base case. This is an induction proof, so there's a base case, and this is the case n equals 1. There's one edge in my graph, and that's what it looks like. There's a graph with one edge. Is the proposition true? G has at least 2 leaves. Yep, this has at least 2 leaves. There we go. Those are my 2 vertices with degree 1. Now here is the induction hypothesis. Let's assume that the proposition is true for every tree with fewer than m edges. So I proved that it was true for a tree with one edge, and maybe I could also show with 2 edges or 3 edges or 4 edges up to some point. But I'll say that maybe m is the first case that I don't know. So I'm assuming, so again, my induction hypothesis, let's assume that the proposition is true for every tree with fewer than m edges. So what do? I'm going to let G be a tree with m edges. And I want to prove that the proposition is true for this tree. Well, there is some vertex v of degree 1. That's what proposition 4 told us. Here we go, I'll label this. How about v will be the vertex at the bottom. And since it has degree 1, there's only one edge that has v as an endpoint. So call that edge vw, and so w must be the vertex that it's connected to. Let's do this. I'm going to form a new graph G' by removing vertex v and the edge it's connected to. So upon removing that, I get the graph G'. Now G' has at least 2 leaves. And this is fantastic. This is where I can use induction. G' has m minus 1 edges. So I know that the proposition is true. It has at least 2 leaves. So in particular, it must have a leaf u that is not w. Now, in this particular example, w is a leaf of G', but in general, I don't really know that w will be a leaf. But since G' has at least 2 leaves, I'm guaranteed about the existence of a leaf that is not w. So let's just find something else. We'll call this u here on the far right. So u is unaffected by the existence or non-existence of that edge that I took away. U is a leaf of the original graph G. So both u and v are leaves of the original graph G. Look at that, 2 leaves, and we're done. Proposition 6. In any simple graph G with distinct vertices A and B, if there is a walk from A to B, then there is a path from A to B. This is an intuitive result. It seems reasonable. If you have a walk from A to B and it kind of loops back on itself, you can get rid of the extraneous cycles and just trim it down to make a path. But remember, this is also the proposition that gave us lemma 1 at the very beginning of this video. Let's see how this works. We will induct on the length of a walk from A to B. So what is the very shortest length of a walk from A to B? Here's our base case. If A and B are connected by a walk of length 1, here we go, A, B, walk of length 1, well, the proposition holds because the walk from A to B must be a path. There is no other way about it. Now, let's assume that this proposition is true for all walks of length less than m. So, suppose that I have a walk from A to B that has length m. So here it is, w equals v1, v2, all the way up through vm, where v0, that's just another name for A, and vm, that's just another name for B. Well, if this w is a path, then we're done. What about the other case? If w has repeated vertices, say vi and vj, then we can make a new walk this way. I essentially cut out the section that goes after I up through and including j. So I make a new walk, w prime, that starts off v1 through vi just like before, and then it cuts out a section, and it picks up with vj plus 1, and it continues to vm. Maybe there's a little bit of a question. vi and vj plus 1, I can only put vertices next to each other if there's an edge connecting them. But in fact, there's an edge connecting vj and vj plus 1, because that was in the original list, and vi and vj are really the same. It's just two different names for the same vertex. And so yes, indeed, there really is an edge from vi to vj plus 1. And so what I have here in w prime is a true walk that goes from A to B, and this is a shorter walk. By induction, there is a path from A to B. I actually kind of hope that you are appreciating the power of the inductive proof in the context of graph theory. These things are kind of neat. Theorem 7. If T is a tree with n edges, then T has n plus 1 vertices. And look at this, we're moving up in the world of results. We're coming up to a theorem. We're moving beyond the lemmas and the propositions. So a lemma is just kind of an uninteresting helper result. A proposition is a fact that's true and kind of interesting. And a theorem, well, that's the real stuff right there. If T is a tree with n edges, then T has n plus 1 vertices. Here are some examples that you can take a look at. You can see that it's true. And I encourage you, even just doodle around a little bit, make a little tree, and see for yourself that the number of vertices is always one more than the number of edges. And it's even true in the trivial case. Even true when there are 0 edges, there is 1 vertex. All right, let's prove this result. We will induct on the number of edges in the graph. Base case. If T has 0 edges, then it has 1 vertex. Check, I believe it. Now let's induct. Assume that the theorem is true for every tree with fewer than m edges. Then we'll show that it's also true for any tree with m edges. So let T be a tree with m edges. There we go. There's a picture of my tree T. Let's choose any edge, VW, and remove it from T. I will label one of these vertices V, and I'll label another one W. And let's remove the edge connecting V and W. Here we go. Fading away. And that's gone. And what I've done is I've ended up creating two different connected components. So there's H1 and H2. So H1, let's just call the number of edges there E1. And H2, let's say that it has E2 edges. Now I know what E1 plus E2 is. The total number of edges is going to be 1 less than the m I started off with, because I, of course, erased the edge that connected the two parts. But I also know by induction how many vertices each component has. So H1 is a smaller tree, so the theorem works for H1. If it has E1 edges, it must have E plus 1 vertices. And H2, if it has E2 edges, I know by induction it must have E2 plus 1 vertices. Let's add those together. Now, I removed an edge, but I didn't remove any vertices. So the total number of vertices in T in the original, that's the number of vertices in H1 plus the number of vertices in H2. When I add together E1 plus E2, I get m minus 1, add the 1 plus 1 is 2, and as a result, we get m plus 1. And that's it. The number of vertices in T is exactly one more than the number of edges. Again, induction. What an idea. And this brings us to our last theorem, well, which is actually a theorem that we've seen before. It's Theorem 2. Maybe Euler's theorem or the existence of Eulerian circuits. Let G be a connected graph. G is Eulerian if and only if every node in G has even degree. First of all, this result is in quotes, vacuously true if G has no edges. So going forward, let's assume that G has at least one edge. We have some kind of edges that we can work with. This is an if and only if. There are two parts to it. We have G is Eulerian, and every node in G has even degree. So I need to show that if the first is true, then the second is true, and I need to prove if the second part is true, then the first part is true. So here we go in the forward direction. Let's assume that G is Eulerian, and we will show that every node has even degree. This direction ends up not needing induction to prove, and it's pretty straightforward. Since it is Eulerian, there is an Eulerian circuit. Okay, let's call that thing V1, E1, V2, E2, V3, E3. So I go vertex, edge, vertex, edge, vertex, edge, all the way, and then I get back to the beginning again with V1. Well, since this is an Eulerian circuit, every edge of G appears somewhere in this circuit, exactly once. So remember, an Eulerian circuit, it travels along every edge exactly once. But that means I also have to hit every vertex of G, and those vertices might appear in this list multiple times. So for example, the V3 that I see there, V3 might appear several times in this list, but with different labels, V10 or V29. But notice that every time it appears because I'm traveling along an edge, I hit the vertex, and then I continue away. And so this V3, by various other names, what is the degree of that going to be? Well, it'll gain 2 for every time it appears in the list. The degree of a vertex will be twice the number of times it appears in the list. And 2 times the number is even, so the degree of each vertex is even. Kind of a neat idea. Let's go in the other direction. Assume that every node in G has even degree, and we will prove that it is Eulerian. This is the more interesting direction, the one that uses induction. In our base case, if G has one edge, it is Eulerian. Now, this one actually, for a base case, this one takes a little bit of thought. What does a graph look like if it has one edge and every vertex has even degree? Well, your initial thought, something like this, does not work. Yes, it does have one edge, but these two vertices each have degree 1. Can you make a graph with one edge and every vertex has even degree? How about this? The graph that has a loop. So it's a single vertex and a single edge. And does this thing have an Eulerian circuit? Yes, it does. I start at the vertex, I travel along the edge, and I end up back at the vertex. There we go, an Eulerian circuit. Base case, handled. Now, the induction hypothesis. Assume, for every connected graph with fewer than m edges, if every node has even degree, then the graph is Eulerian. That's our induction hypothesis. So, suppose there's a graph G that's connected, it has m edges, and every node has even degree. How am I going to find an Eulerian circuit? Well, here's a picture to help us. Consider this graph G. It has m edges, and every vertex has even degree. Well, I know that G contains a cycle C. And so maybe I will identify it, bring it out here. There's cycle C. If I see it in the graph itself, it looks something like this. But any cycle will do. I just identify some cycle in the graph. Next, I'm going to form G prime by removing C from G. What does it mean to remove a cycle? It means I'm going to remove every edge that's in C, And also, I'm going to remove any vertex that lives only on C and not in the rest of the graph. So the result in this case looks like this. And I actually end up with two different connected components. Now, G prime will consist of connected components H1, H2, on and on, up through HK. And I don't know how many different connected components I'll have. It might be one, or it might be several. But now what's important is that each of these connected components is a smaller graph. It has fewer edges. So I can use induction, and I can apply my induction hypothesis. Moving things up a little bit. By induction, each component has an Eulerian circuit, C1, C2, up through CK. So in this example with H1, there's an Eulerian circuit C1, and H2 has an Eulerian circuit C2. Each of these meets my original cycle C at some vertex, say V1 through Vk. In the example, V1, maybe that's vertex 3. See, 3 is on the cycle, and 3 is on H1. So V1 equals 3. I might have other choices for V1, but that one works. And in component H2, looks like we have 8. So V2 is vertex 8. We can now insert Eulerian circuit Ci into the cycle C at vertex Vi to form an Eulerian circuit for G. So for example, let's say I'm going through my circuit C. I might start at 1, and I come down to 2. I come across to 3. Once I hit that V1, I come over to H1, and now I know I can complete an Eulerian circuit. So maybe something like this. I do an Eulerian circuit through C1. Got that. I return back to my cycle. I continue on. I get to 8, which is my V2. I come over to H2. I can complete a circuit there, come back, and complete my way around the cycle. And that's it. So as I complete my way around the cycle, at various times I jump over to the different connected components, I complete an Eulerian circuit, and I come back to the cycle, and it's all good. I now have created an Eulerian circuit for the entire graph G. Okay. Well, there was a lot in this lesson, I know. But here's really what I want you to take away. I want you to come away with an appreciation for the kinds of results that one considers in graph theory, and an understanding for how one proves graph theory results, and an appreciation for the application of inductive proof in graph theory. All right, I've said enough already. We'll stop here.